Hey guys, so we're going to start looking at exponential growth and decay functions and their graphs today. To start us off, let's look at kind of these warm-up questions I have here set up because earlier in the year we talked about transformations of functions, and those skills not only are great test-taking strategies for matching equations with their graphs on an EOC or an ACT, they're great things to know, but they apply here in our lesson as well, and they can help us as we work through these lessons. So I want to review that really quick. The directions, they describe the transformations of each graph and given that the parent function is f of x equals x squared. So just talking about our plain old parabola, how these guys would be different. So number one, if g of x was the quantity of x plus 3 squared minus 1. So the squared piece right there is still just giving us our parabola shape. The question is, what kind of transformations have happened? So the first thing is the squared is on this entire parentheses of x plus 3. So what does the plus 3 do? So if you can think back to those lessons, if you have addition inside, whether that's inside your parentheses or inside absolute value bars or inside a radical on a radical function, a square root function, the inside is going to make it move from side to side, but in the opposite direction that you may think. So this plus 3, we might think it moves to the right 3 places, but it's actually going to shift my graph to the left 3 units. I'm going to say 3 units. So I already know I have a plain old parabola that's actually been shifted to the left 3 spaces. We also have this minus 1 at the end. If you have addition or subtraction at the end, that really shifts it up or down on our for our parabolas. So this minus 1 is going to shift it down 1 unit. So those are your 2 transformations on number 1. Just looking at from the plain old parabola, f of x equals x squared, how this first one is different. It's been shifted 3 units left and 1 unit down. And these are very popular questions on the EOC, so these are worth reviewing. Number 2, doing the same thing, comparing it to that original graph, f of x equals x squared. How is g of x equals negative 2x squared different? Well, you've got this negative in front, and that's my favorite transformation because a negative makes it reflect or flip upside down. So instead of a nice happy parabola, I've automatically now got an upside down frowny face parabola. And then the 2 is also different. It's a separate transformation. The 2 in front, if you have a whole number in front of your function, it's going to stretch it vertically. So this is going to become a skinnier parabola. So write skinny slash, it's called a stretch. So if I think about pulling it and stretching it vertically, it's going to get skinnier. And number 3, doing the same thing, comparing it to the original parent function of just a plain old parabola, x squared. How is g of x equals 3 times the quantity of x minus 1 squared? How is that different? Well, again, you've got that 3 in front. That whole number in front is going to stretch it or make it skinny. We've got some addition or subtraction inside our parentheses there. So x minus 1, again, it kind of shifts it left to right, but opposite of what you think. So not towards the negative, but actually to the right 1 unit. And that's it. Again, the squared is making our parabola shape. It's still keeping it in that same function family. So again, this is a review of transformations, some quick tricks. Again, this is just creating like a quick sketch in our brain of what the function looks like. So if I was on an EOC test, I could look at multiple choice answers quickly, eliminate, or maybe find my answer just by knowing the transformation tricks here. Okay, let's check out graphs of exponential growth and decay functions. So I'll give you a little bit of knowledge here. So an exponential function is literally going to shoot up like a rocket ship. It's going to grow exponentially. So, and here's what our functions look like. Y equals a times b raised to the x minus h plus k. So one thing I always tell my students is in an exponential function, x will always be the exponent. X is always the exponent. in an exponential function. So I know sometimes these guys look a little weird, and we were just talking about quadratics a moment ago. In a quadratic, the ones we were looking at a minute ago, the exponent was 2 squared, right? So I made a parabola. So we are talking now about exponential functions, and x, our variable, will always be our exponent. So there's a lot of pieces here. So let's walk through it. First, let's talk about a. So first of all, if a is negative, it's going to reflect it. I'm going to do these in different colors so we can keep track of all these pieces. If a is negative, just like in the warm-up, it flips it, it reflects it. So I'm going to write reflect because that's kind of the better math term. It's going to reflect it upside down. So instead of my rocket ship going up, it's going to be a rocket ship shooting down. Okay. Another thing about a, if a is greater than 1, same thing. It's going to stretch it. It's going to be a skinnier stretch. It's going to be a skinnier rocket ship. And if a is less than 1, if it's a fraction, it's going to compress it. So we didn't have a compression example on the warm-up there, but instead of stretching, it compresses, which means it gets wider. Think about Play-Doh. If I squished Play-Doh, it would get wider between my hands. All right, so that's A. Let's see about B. So you can see from the title, exponential growth or decay. So growth is my rocket ship. Decay is like the flipped one, crashing, burning, right? So if B is greater than 1, then it's going to be growth, exponential growth. If B is less than 1, but let's say that it's between 0 and 1, because we don't really want to say a negative. So if it's a fraction, if it's a decimal, it's going to be decay. It's going to get smaller and smaller and smaller, okay? Moving on, let's use red, because I'm going to look at H. So H, just like in the warm-up, it's going to move it side to side. X has still got to be there. X has always got to be there to represent an exponential function. X is always the exponent. But H is going to move it left to right. So if H is, it's going to move left, it still goes backwards. So left if it's got addition, and right if it's like a subtraction problem there. You can see from our basic function, it's already X minus H. So this one is set up to move right, like the basic function. If it got changed to a plus, then we would be subtracting a negative number and it would move left, okay? I'm gonna erase that. Let's move on to K. So just like the other transformations, all of our function transformations do really translate across all of our functions. K is going to represent our horizontal asymptote. Horizontal asymptote. So some of you may have seen the word asymptote before. An asymptote is an imaginary line, or looking at our exponential function, it's going to be horizontal. It's going to be an invisible line. I think I said imaginary. It's an invisible line that our graph is going to get closer and closer and closer to, but never touch. And that's because at that horizontal asymptote is when our denominator would become 0 and the function wouldn't exist. Fancy stuff. So K is going to represent our horizontal asymptote. Simple as that. Y equals the number. So if it was 5 right there, Y equals 5 on the y-axis at 5, I would have a horizontal asymptote that my graph would get closer and closer and closer to, but never ever touch. It would get really close, but never actually come to it. The other thing, it does still apply our transformation. So you're still going to see if you have like plus a number, it's going to move up. So let's write, it's still going to move up if you have plus, or your graph is going to look like it moved down if it was minus right there. So it's still shifting it up and down that last term there. So we dissected a lot. So this is your basic exponential function. X is your exponent for your exponential functions. Okay. All right. Right below that, we have domain and range. Let's talk about that for 1 second. Do not be afraid. Domain, it's so easy because for all of our exponential functions, do you hear me? All of them, Every problem I give you this week asking domain, they have the same answer. Okay, so if I have a rocket ship, let's look at our rocket ship. Domain, X values. So as I approach the left, it's going forever. As I approach the right, I know it's going up, but it's also inching out, inching out, inching out, inching out forever. So for all of our exponential functions, the domain is all real numbers, all reals, or you could use the cursive R. We can also use interval notation. I forget which one Delta Math uses, but your domain is all real numbers for exponential functions every time. Okay, for your range, now we're going to use our function a little bit. It's kind of easy to see the graph, and we're going to look at examples here in a minute. We'll look at the graph, and I'll show you your range. Of course, that's your y values. We're looking at your y-axis. How low does your graph go? How high does it go? So our range, if we're using just our function, just our equation, we can use some tricks. If A, and I'm talking about this little baby A in front, if A is positive, if you have a positive exponential function, which looks like the rocket ship in orange, we're actually going to use our K value, the asymptote. It's going to go from K to infinity because it's going to be a rocket ship. It's going to go from your horizontal asymptote to infinity, okay? If A is negative, which let's remember, if the front of my function is negative, it's been flipped or reflected. So I've got the crash and burn decay graph over here that I doodled in purple. Then again, we're going to use our K value, but we always talk about how low to how high. So it's actually going to go from negative infinity to K. Whatever your K value is, whatever the last number is in the function, that's your range, okay? So I know that's a lot to digest. Let's look at some examples, because what we did, we dissected our exponential functions, all the pieces, the transformations they do. We threw in asymptotes. That's new. So let's look at some things in action. These are the types of problems you're going to see on Delta Math. This first one, looking at the function f of x equals -2 times 2 raised to the x plus 4. So on Delta Math, they're going to give you the function and they give you the graph. So let's tie them in. Let me show you some connections, build you a good foundation. So first of all, I know that this has been reflected. You see that? So instead of a usual rocket ship, this has been flipped upside down and now it's crashing and burning. I need to come up with a new term for crash and burn. But let me erase this. So I know it's been reflected. The 2 here means that it's a growth, but it's been flipped. So we started off with a flat line and it was growing, but the negative in front made it flip. So the 2 with the exponent, that means growth as opposed to decay. Moving on, don't let that bother you. X is my exponent, so this is an exponential function. And the plus 4 here meant that it moved up 4 units. So it's not sitting on my axis, it's up 4 units. So take a look at that picture there. And so what you're going to do on Delta Math, you've got all these drop-down boxes. A lot of them are going to be the same for all of our exponential examples. So first off, your first drop-down box is the function f of x is an exponential. You have x as your exponent, exponential. It's an exponential function with a horizontal asymptote. So that invisible line is right here. Okay, that's my invisible asymptote line. See, my graph gets closer and closer and closer to it. It's wherever it levels off, if that helps you. All right, we got to actually fill this in because I started us off. I said the horizontal asymptote of, it is always going to start with y equals. And remember above, our horizontal asymptote is y equals our k value, the last one. So we got 2 options here. You can look at your graph, 4, or you can look at your function and see 4, or you can look at your graph and see that it's leveling off where y is equal to 4. So fill that in. You should have a 4 right there. The range of the function is, now what did I say about range? It's going to be whether your a is positive or negative, On our function over here, a is negative. So our range is going to be from negative infinity to whatever our k value is, which is 4. Negative infinity to 4. Now look at the graph. The range values, the y values, up and down. How low does this go? Well, all the way down to negative infinity. How high does it go? It's going to go up to 4. Never, ever actually touching 4. So your range is from negative infinity to 4. And it is increasing or decreasing from left to right. As I go left to right, it is decreasing. It is decreasing on the domain of negative infinity to positive infinity. Now that one is always going to be the same, right? Domain, what did I say before? The domain for all of our exponential functions is all real numbers every time. Because let's look at it. As we approach left, where's it going? Infinity. As we approach right, where's it going? It's going to slowly inch out forever and ever, never, never, never. And eventually, if we had infinity forever, it would go to positive infinity on the x-axis. So that one is there always forever. All real numbers, negative infinity to positive infinity. And the last statement we've got to fill in is about end behavior. So the end behavior on the left side. So as I look at the left side, as x approaches negative infinity, what is y doing? Well, y is going to continue to approach 4. That's on the left side. As x goes left, y is approaching, getting closer and closer to 4. On the other side, on the right side, as x approaches positive infinity, as x keeps going that way, where's the y going? The y is going straight down, forever and always. Y is approaching negative infinity. Now, if some of you thought, oh, it's approaching 3, I get it. I get where you got that. But what is 3? 3 is on the x-axis. 3 is an x value. We're talking about y's. Where is it going to go as we keep inching out? It's going to go all the way to negative infinity, okay? So it's the ones that I filled out here on the lines, exponential, horizontal, y equals the domain of negative infinity to positive infinity. In behavior on the left side as x approaches negative infinity, and right side as x approaches infinity, those should be the same every time, okay? Now, I didn't include them on the next example, so let's see if we can remember what goes where. Number 2, let's see what's going on. So the 1/3 is my base, and that tells me this is a decay. It is getting smaller and smaller. See how it's like dropping? It's leveling off, getting smaller and smaller as we move left to right. X is my exponent, so this is an exponential function. All right, so I found a mistake on my notes, but I'll have it fixed by the time y'all have this lesson. So this should say -2. Your paper should say -2 at this point. So the -2 is telling me it's been shifted down 2 units, okay? So let's fill in our blanks. The function f of x is an exponential function. You have another option there in your drop-down list of logarithms. We're not to logarithms yet, okay? So all the examples you see should be exponentials. A function with a horizontal asymptote. So we should have an invisible horizontal line where our graph is getting closer and closer, leveling off at, of, since it's horizontal, y equals, so we can look at our graph, where is it leveling off, or you can look at your function, what the last number is, -2. You can see on my graph, it's leveling off down there at -2. The range of the function is from my a up here in the front is positive. The beginning of my function is positive. So it should be from my k value or my asymptote to infinity. Or you can look at your graph, your range on your y-axis. How low does it go? It's going to go only down to -2. How high does it go? Infinity, okay? -2 to infinity is your range. It is decreasing left to right. Think about reading your graphs left to right. It started off high, it's going down, decreasing. On the domain of all real numbers, negative infinity to positive infinity. Your domain is all real numbers for every exponential function. Let's look at it. Let's talk about it. How far left is it going to go? I know you're going to see it going up, but let's talk about how it's inching out to the left a little bit each time. It's going to eventually go all the way left. And obviously, it's going to go all the way right. All real numbers every time. The end behavior on the left side, if we're talking about left side, we want x is approaching negative infinity. So on the left side, what is it doing? Y is going up, 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 up. Y is going to approach positive infinity. The end behavior on the right side, as x approaches positive infinity, the y value is getting closer and closer to -2. Okay. All right, number 3, you have your function, you have your graph. The function is exponential. I know because my x is my exponent with a horizontal asymptote. I can see I have an invisible horizontal line that my graph is flattening off at, getting closer and closer to, of y equals, what is it getting closer and closer to? +3, which is also the last number on the function. The range, your y values, how low does it go? Well, it's going to go all the way to negative infinity. How high does it go? It's only going to reach 3. We do have a negative here, so we said our range would be from negative infinity to our k value, or that's negative infinity to 3, which is what we see there on the graph. Negative infinity to 3 is my range. It is increasing from left to right, is going up. It is hitting this invisible asymptote, but it is still getting closer and closer on the domain of all real numbers. It's going to go all the way left and all the way right. The end behavior on the left side, as x approaches negative infinity on the left side, my graph, the y values are approaching down, negative infinity forever, going down, down, down. And I know my infinity signs are beautiful. As the end behavior on the right side, as x approaches positive infinity, as it goes to the right, my y is getting closer and closer to 3. Last one, number 4. Your function is just f of x equals 2x. Super simple. Sometimes the most simple problems on Delta Math are the ones that give my students the most trouble. So 2 is just telling me that it's growth. X is my exponent, so it's an exponential function. No other transformations. So this function is exponential with a horizontal asymptote of y equals, where is it leveled off at? Where is it leveled off at? 0. What's the last number here on my function? 0. So you got a horizontal asymptote at y equals 0. Your range, how low does it go? Well, it's going to go to 0. How high is it going to go? Infinity. 0 to infinity. It is clearly increasing from left to right on the domain of all real numbers from negative infinity to positive infinity. The end behavior on the left side, as x approaches negative infinity, what's your y's doing? Left side, y is approaching 0. On the right side, x is approaching positive infinity. What's y doing? As I go to the right, y is going up, up, up to infinity. Okay, so take some time on those. Again, you got lots of drop downs on Delta Math. I modeled it right here. All of these blanks are all the drop downs that you get to fill in. So you do have some multiple select there, but there is a lot to select. So you got to do it carefully, because if you miss one box, you got to restart your whole new problem. Remember, on an exponential function, it can be growth and it can be decay, but the x is always the exponent. And your graphs look like rocket ships, or they are decaying. They're getting smaller and smaller and approaching that invisible horizontal asymptote. Reach out if you have any questions. I know this is a lot to digest.